Next, we're going to talk about compressors and pumps. Compressors and pumps are used to increase fluid pressure by putting in work. Compressors are used for gases and pumps are used for liquids. For compressors and pumps, heat transfer is usually negligible, and we generally assume the process to be adiabatic. Change in potential and kinetic energies are also often neglected. Air at 100 kilopascals and 280 Kelvin is compressed steadily to 600 kilopascals and 400 Kelvin. The mass flow rate of the air is 0.02 kg per second, and a heat loss of 16 kilojoules per kg occurs during the process. Assuming the changes in kinetic and potential energies are negligible, determine the necessary power input to the compressor. Assume ideal gas behavior and take specific heat at constant pressure as 1.005 kilojoules per kg Kelvin. So our inlet conditions, the pressure at the inlet is 100 kilopascals, temperature at the inlet is 280 Kelvin. For our exit conditions, exit pressure is 600 kilopascals and exit temperature is 400 Kelvin. The mass flow rate is given as 0.02 kg per second. And we'll write our heat flow as minus 16 kilojoules per kg. It's negative because this is heat loss, and according to our convention, heat moving from the system to the surrounding is negative. We've also been told that change in kinetic energy and change in potential energy is negligible. We can therefore write our energy equation for this process as heat flow plus inlet enthalpy equals exit enthalpy plus work done. We can rewrite this as work done equals heat flow plus inlet enthalpy minus exit enthalpy. And since we're assuming ideal gas behavior, we can write the inlet enthalpy minus the exit enthalpy as the specific heat at constant pressure into inlet temperature minus exit temperature. Substituting all our known values, we obtain minus 136.6 kilojoules per kg. This is the work done per unit mass of air that passes through the pump, and it is negative, meaning work is done on the fluid. To calculate the rate at which work is done, we multiply the work done per unit mass by the mass flow rate. We can do away with the negative sign now because we already know the direction of our work. For the rate at which work is done, we obtain 2.73 kilojoules per second, or 2.73 kilowatts, and this is the required power input for the compressor. Air flows steadily at the rate of 0.4 kg per second through an air compressor, entering at 6 meters per second with a pressure of 1 bar and a specific volume of 0.85 meters cubed per kg, leaving at 4.5 meters per second with a pressure of 6.9 bar and a specific volume of 0.16 meters cubed per kg. The internal energy of the air leaving is 88 kilojoules per kg greater than that of the air entering. Cooling water in a jacket surrounding the cylinder absorbs heat from the air at the rate of 59 kilojoules per second. Calculate the power required to drive the compressor and the inlet and outlet pipe cross-sectional areas. So we've been given our mass flow rate, which is 0.4 kg per second. Our inlet conditions, we have inlet velocity 6 meters per second, inlet pressure 1 bar or 100 kilopascals. Specific volume at the inlet is 0.85 meters cubed per kg. For our exit conditions, we have exit velocity as 4.5 meters per second. Exit pressure is 6.9 bar or 690 kilopascals, and the specific volume at the exit is 0.16 meters cubed per kg. We were told that the internal energy at the exit is 88 kilojoules per kg greater than the internal energy at the inlet. So we can write this as UE minus UI equals 88 kilojoules per kg. And we were told that the rate of heat transfer is 59 kilojoules per second. Again, we write this as a negative value because this is heat lost from the system. To solve this problem, we can use our energy equation, or we can multiply through by the mass flow rate and write this equation using the rates of heat transfer and rate of work done instead. Making the rate of work done or power the subject, we can write our equation as this. There was no mention of any change in the potential energy or height, so G into Zi minus Ze equals 0. Hi minus He, the difference in the specific enthalpies, becomes Ui plus PiVi minus Ue minus PeVe, or Ui minus Ue, the change in the specific internal energies, plus PiVi minus PeVe. So the power becomes this. We know all of these parameters, so we just substitute the values. Also, let's not forget to divide our velocity terms by 1000. So from this, we obtain the power as minus 104.36 kilojoules per second, or minus 104.36 kilowatts. And it is negative because this is the power required to do work on the fluid. To obtain the inlet and exit cross-sectional areas, we use the expression for mass flow rate, which is velocity times cross-sectional area divided by specific volume. So the cross-sectional area is equal to the mass flow rate multiplied by specific volume divided by velocity. So the cross-sectional area of the inlet is equal to the mass flow rate times the specific volume at the inlet divided by the velocity at the inlet. Substituting all the values, we obtain this cross-sectional area as 0.057 meters squared. And we do the same for the exit, so we obtain the cross-sectional area at the exit as 0.014 meters squared. You can always use dimensional analysis to check whether your units correspond or there's some conversion you need to do. The third steady flow device we'll be considering is heat exchangers. Heat exchangers are devices where two moving fluid streams exchange heat without mixing. Heat exchangers typically involve no work interactions and negligible kinetic and potential energy changes. So for a heat exchanger, our energy equation becomes heat flow plus specific enthalpy at the inlet equals the specific enthalpy at the exit, or heat flow equals the difference in enthalpies. The next steady state device we're going to be looking at is turbines. In steam, gas, or hydroelectric power plants, the device that drives the electric generator is the turbine. As the fluid passes through the turbine, work is done against the blades which are attached to the shaft. Heat transfer from turbines is usually negligible. Air at 101.325 kilopascals and 27 degrees Celsius is taken into a gas turbine power plant at a velocity of 150 meters per second through an opening having a cross-sectional area of 0.175 meters squared. The air is expanded through a turbine and exhausted at 0.18 megapascals and 150 degrees Celsius through an opening of cross-sectional area 0.125 meters cubed. The power output is 400 kilowatts. Calculate the net amount of heat added to the air in kilojoules per kg. Assume ideal gas behavior and take the gas constant as 0.287 kilojoules per kg Kelvin, and the specific heat at constant pressure as 1.005 kilojoules per kg Kelvin. So for the inlet conditions, we have inlet pressure 101.325 kilopascals, inlet temperature 27 degrees Celsius or 300 Kelvin. Inlet velocity 150 meters per second. And inlet cross-sectional area 0.175 meters squared. For the exit conditions, we have exit pressure 0.18 megapascals or 180 kilopascals. Exit temperature 150 degrees Celsius or 423 Kelvin. And exit cross-sectional area 0.125 meters cubed. Our power output is 400 kilowatts or 400 kilojoules per second. To convert this power output to work done per unit mass, we divide by the mass flow rate. But we don't know the mass flow rate. We know mass flow rate equals velocity times cross-sectional area divided by specific volume. So we can apply the inlet parameters to this. First, we need to find the specific volume at the inlet. To do that, we use the ideal gas equation PV equals RT, or V equals RT divided by P. And using this, we obtain the specific volume at the inlet as 0.85 meters cubed per kg. And so our mass flow rate is 30.88 kg per second. And we can now use the mass flow rate to calculate the work done per unit mass. And for this, we get 12.95 kilojoules per kg. We're going to write this as a negative value because work is done on our fluid. Using our energy equation, we can find the heat supplied to the air. Since we're assuming air is an ideal gas, we can say HE minus HI equals Cp into Te minus Ti. Also, there's no change in height or potential energy, so G into Ze minus Zi equals 0. So our energy equation looks like this. We don't know the exit velocity, but we can obtain it using the expression for mass flow rate. And since the mass flow rate is the same at the inlet and the exit, we can write inlet velocity multiplied by inlet cross-sectional area divided by the specific volume at the inlet equals exit velocity multiplied by the exit cross-sectional area divided by the specific volume at the exit. So we obtain an expression for exit velocity. But we still need to find the specific volume at the exit. And again, we use our ideal gas equation. So for our exit specific volume, we obtain 0.67 meters cubed per kg. And now we can find the exit velocity, and this gives us 165.5 meters per second. Now that we have everything we need, we can find the heat flow using our energy equation. And from this, we get 188.85 kilojoules per kg. And this is the net amount of heat added to the air in kilojoules per kg. A steam turbine is supplied with steam at the rate of 200 kg per hour and at pressure and temperature of 5 bar and 200 degrees Celsius respectively. Assume the velocity of steam entering the turbine is negligible, and given that the expansion of steam within the turbine is adiabatic and steam leaves with a velocity of 20 meters per second, the condition of steam at the exit is 0.1 bar and 0.9 dryness fraction. After leaving the turbine, the steam enters a condenser where it is condensed and leaves as saturated liquid at 0.1 bar. If there is no heat transfer between the condenser and the atmosphere, calculate 1. The power driven by the turbine, 2. The heat transfer rate from the condensing steam. We know our mass flow rate, 2000 kg per hour. To convert this to kg per second, we divide by 3600, which is the number of seconds in 1 hour. And we get our mass flow rate as 0.556 kg per second. For the inlet conditions, we have P1 equals 5 bar or 500 kilopascals. T1, the inlet temperature, is 200 degrees Celsius or 473 Kelvin. And for the exit conditions, we have exit pressure 0.1 bar or 10 kilopascals, dryness fraction 0.9, and exit velocity 20 meters per second. To calculate the power developed by the turbine, we first find the work done per unit mass of steam, and we use our energy equation. We can rewrite it this way, making the work done the subject. This expansion is adiabatic, so the heat transferred to the steam is equal to 0. The inlet velocity is negligible, so we can write it as 0. And there is no change in height or potential energy. So our energy equation becomes reduced to W equals HI minus HE minus VE squared divided by 2. We can find the inlet and exit enthalpies using steam tables. So at the inlet pressure 500 kilopascals, the saturation temperature is 151.83 degrees Celsius. The inlet pressure 200 degrees Celsius is greater than this, so the steam is superheated. Using superheated steam tables at 500 kilopascals and 200 degrees Celsius, the specific enthalpy is equal to 2,855.8 kilojoules per kg. At the exit, the steam is a saturated liquid vapor mixture with a dryness fraction of 0.9. So the exit enthalpy equals HF plus XHFG. At 10 kilopascals, HF, which is the enthalpy of saturated liquid, is 191.81 kilojoules per kg, and HFG is equal to 2,392.1 kilojoules per kg. So we obtain our exit enthalpy as 2,344.9 kilojoules per kg. And substituting all our values into the energy equation, we obtain the work done per unit mass of steam as 510.7 kilojoules per kg. We can see that we have a positive value because in a turbine, the working fluid does work in turning the blades of the turbine. To calculate the power generated, we multiply the work done per unit mass by the mass flow rate. And for our power, we obtain 283.95 kilowatts. Now for the heat transfer rate from the condensing steam. The condenser is simply a heat exchanger, so we're going to use our energy equation for a heat exchanger. The inlet conditions for the condenser will be the exit conditions for the turbine. And at the exit of the turbine, our steam had an enthalpy of 2,344.9 kilojoules per kg. So for the condenser, inlet enthalpy equals 2,344.9 kilojoules per kg. Now for the exit conditions. At the exit, our working fluid is a saturated liquid at 0.1 bar or 10 kilopascals. So the exit enthalpy will be HF at this pressure. And from our steam tables, we obtain HF to be 191.81 kilojoules per kg. So the heat transfer equals 191.81 minus 2,344.9. And this gives us minus 2,153.09 kilojoules per kg. And from this, we can obtain the heat transfer rate by multiplying with the mass flow rate. So for heat transfer rate, we obtain 1,197.1 kilojoules per second. The final steady state process or device we're going to be considering is throttling valves or the throttling process. A throttling process occurs when a fluid flowing in a line suddenly encounters a restriction in the flow passage. The result of this restriction is a sudden pressure drop in the fluid, as it is suddenly forced to find its way through a smaller passageway. Throttling valves are any kind of flow restricting devices that cause a significant pressure drop in the fluid. Throttling is usually assumed to be an adiabatic process. There is no work done, and the change in potential energy is often negligible. Even though the exit velocity is often significantly higher than the inlet velocity, the increase in kinetic energy is usually still insignificant. So for throttling, our energy equation is reduced to just the inlet and exit enthalpies. And because of this, throttling is usually considered to be an isenthalpic process or constant enthalpy process.